Welcome to the fourth lecture in Microeconomics in summer semester 2020. Today we are going to deal with Chapter 4, the optimal choice of the household. The material we will cover today you may find in our coursebook Intermediate Microeconomics in Chapter 5, as well as in Chapter 3.6 to 3.8 and Chapters 4.4 and 4.5 on marginal utility and marginal rate of substitution. In Lecture 2, we learned that a household wants to choose the best consumption bundle that it can afford. The question then were what is best and what is meant by afford. Now we know what it is. The best consumption bundle is the one that gives the highest utility. The consumption bundles that the consumer can afford are all those located in the budget set. However, here we are going to deal only with the assumption that the household spends its entire budget, and hence we are going to look for optimal consumption bundles only on the budget line. A consumer's optimal choice problem can be formulated either as a utility maximization problem or as an expenditure minimization problem. By utility maximization, we mean that the household has a certain budget available which it wants to spend entirely on the consumption of a bundle of goods. And the aim of the household here is to spend this money to maximize its individual utility. With expenditure minimization, it is the other way around. Here, a household exactly knows which utility level it wants to achieve and is looking for a smallest possible budget to spend to meet this aim. To illustrate our graphical solution here, let us look at an example. Assume that you have a little brother who is a great fan of Lord of the Rings, and you have made him a gift of 100 euros to his birthday. And now your little brother wants to spend all this money of 100 euros on buying an army of little toy orcs and little toy elves. So, little toy orcs will be our good one here. Little toy elves will be good two. Let us have a look at utility maximization of your little brother. The problem can be written down algebraically as follows. Maximize the utility function u of x1, x2, subject to the budget constraint. The budget constraint here is the price of orcs, of one orc soldier, times the number of orc soldiers that your brother wants to buy, plus P2, which is the price of one elf soldier, times the number of elf soldiers that your brother wants to buy. And M on the right side is the budget that your brother wants to spend entirely on buying the soldiers. So it's 100 euros here. The budget line, which we have discovered or learned to know in Lecture 2, is depicted here in the right diagram. It is a downward sloping line in the x1, x2 coordinate system. Your brother's utility is represented by the system of indifference curves here in the other figure. We assume that your brother has well-behaved preferences. So he is willing to substitute between elf soldiers and orc soldiers. However, he will most likely feel best if he has approximately the same number of orc soldiers on the one hand and elf soldiers on the other hand, such that he can construct a battle which really makes sense. Let us now bring these two figures together. Here we see the constraint. This is the budget constraint. Every point that is located on this line is not only affordable, but it is a consumption bundle that your brother can buy, spending the entire budget of 100 euros. Your brother maybe has big dreams. He wants to create a battle of huge armies. So maybe 90 or 80 elves versus 80 orcs. Buying such a bundle would represent this utility level. It is really high for your brother. He would be really happy with it. However, unfortunately, with the budget he has, he cannot afford it. The same holds for all these three other indifference curves which we see here in the diagram. On the other hand, if your brother would decide to buy much less elf soldiers and much less orc soldiers, he will maybe get to an indifference curve, which is represented by this one, and point A, for instance. So here you would have maybe 5 orcs and 10 elves. In this point, he would be just as satisfied as dealing with an extreme uneven distribution of the orc army and the elf army. So for instance, in point B here, he would have a lot of elves, but a few orcs. And on the other hand, he would be as well off as before in point A and point B, with an army that consists of a lot of orcs and just a few elves. So we want him to spend his entire budget on this army of orcs and elves. What he can afford is located all on the budget line. So we can move now to higher indifference curves from the left to the right. Step by step, we will go up, and finally reach one indifference curve which has only one point in common with the budget line. And this is, according to our theory, the optimal consumption bundle. So here, your brother, reaches the highest possible utility given his budget of 100 euros. And this is represented by U of x1 star, x2 star. x1 star is the number of elves, x2 star is the number of orcs. By consuming the bundle x1 star, x2 star, your brother would get the highest possible utility, U star, given his budget M. Now from this graphical solution we can infer what, according to our model, must hold in the optimum. We see that there is only one point in common between the indifference curve, represented in green here, and the budget line in black. So this means that in this point, the slope of the budget line must be equal to the slope of the indifference curve. Let us now have a look at the expenditure minimization. This is the same problem, just from another perspective. Assume that your brother has got more money to his birthday than 100 euros. So maybe he has got 250 euros. And now he wants to buy so many elves and so many orcs that he can reach a certain utility level which he already knows. It is pretty hard to imagine. However, maybe he remembers that there was a battle which he had with a friend of him, and he wants to just exactly reconstruct this to get the same feeling, so to get the same joy. Right, so here the problem is he wants to minimize his expenditure, which is represented by the function p1 times x1 plus p2 times x2. And the constraint now is that he wants to reach a certain utility level u bar. So we just switch constraint and objective function. The constraint is now represented by a certain indifference curve, which is here on the right. And this, in our example, shall be the same indifference curve which your brother has reached in the utility maximization problem. Okay, on the other hand, your brother can spend different amounts of money on buying the orcs and the elves. And different expenditure levels are here represented just by parallel lines, each of them representing a certain budget. So what changes here is M. The prices, P1 and P2, remain constant, and correspondingly the budget lines shift parallel to the upper right corner of this diagram. Let us now bring these two figures together. In the beginning, your brother knows he wants to achieve exactly this utility level. So, Maybe he first of all tries to calculate, okay, how much utility I will get if I spend this amount of money. And he sees, okay, this will not suffice. Then he goes up and up, increasing the numbers of soldiers from the Elven and Orcish army, until finally he reaches this optimal expenditure, in which he exactly has one point in common between his budget line and this indifference curve. From this point, it doesn't make any sense for him to increase the expenditure more, because increasing the expenditure more would result in a higher utility level. So he doesn't want to achieve a different one. He just wants to get exactly this one utility level. Again, in this tangent point, the optimal consumption bundle is x1 star and x2 star. By setting the utility level at the same value as we had in the utility maximization problem, we achieve exactly the same bundle. By consuming the bundle x1 star and x2 star, your brother gains the wanted utility, spending the lowest possible budget, M. Again, here the optimality condition is that the slope of the indifference curve must be equal to the slope of the budget line. There is a relationship between utility maximization and expenditure minimization, and this relationship is called duality. To wrap it up, let's state this again. So in utility maximization, by consuming the bundle x1 star, x2 star, the household gains the highest possible utility U star, spending its budget M. In expenditure minimization, it's just the other way around. By consuming the bundle x1 star, x2 star, the household gains the wanted utility level U bar, spending the lowest possible money M star. What can we infer from this graphical solution? We can state that if an inner solution exists and indifference curves are well behaved, so they are monotonic, strictly convex, and differentiable, then the optimal consumption bundle is the point in which the slope of the indifference curve will be exactly equal to the slope of the budget line. Now let us formulate the optimality condition which we have found graphically, algebraically. What is the slope of the budget line? We know that the budget line results from rearranging the budget equation for x2. So this is just this function. And the slope of it, it's easy to determine. We just take the first derivative with respect to x1 and get that the slope of the budget line is minus p1 over p2. What is the slope of the indifference curve? This is a little bit harder to determine because the indifference curve is just a graphical representation of a utility level in the x1, x2 diagram, while the utility function itself is a function of two variables. So let us compute the differential of the utility function for a certain utility level U bar. The differential is the first order partial derivative with respect to x times the change in x1 plus the first order partial derivative with respect to x2 times the change in x2. And on the other side of this equation will be 0 because the utility does not change along an indifference curve. Rearranging this equation for the ratio dx2 divided by dx1 will result in a negative value. And this negative value is the slope of the indifference curve, which you can see here on the slide. This negative value is called the marginal rate of substitution. So what you can memorize is the slope of the indifference curve is the marginal rate of substitution. Let us bring these two concepts together now. We know in optimum must hold the slope of the indifference curve must be equal to the slope of the budget line. And we know both now. So this is the slope of the budget line. Here we see the slope of the indifference curve. and in the optimum it must hold the following optimality condition. The marginal rate of substitution is equal to the negative ratio of the prices. The marginal rate of substitution has an economic interpretation. It is the slope of the indifference curve. However, it also tells us by which proportion the household is willing to substitute one good for the other. We can sum it up in the following way. The private household would only agree to give up 1 unit of good 1 if it would be compensated with the absolute value of the marginal rate of substitution, units of good 2. The idea here is that the household wants to remain on the same indifference curve and hence on the same utility level as before it agreed to give up 1 unit of good 1. On the other hand, of the optimality condition, we have the negative price ratio, which is the slope of the budget line. This has also an economic interpretation. If a private household with a constant budget M is forced to consume 1 unit less of good 1, the money it does not spend on this unit suffices to consume P1 over P2 more units of good 2. Here, the household spends its whole budget M. Now, in the optimum, these two terms must be equal. Another possibility of interpreting it is to change to increasing a certain good and what will be the effect on the other goods consumption. So the slope of the indifference curve is still the marginal rate of substitution, and the absolute value of the marginal rate of substitution is the amount of good 2 that a household is willing to pay for 1 extra unit consumption of good 1. On the other hand, P1 over P2 is the amount of good 2 that a household must pay for 1 unit extra consumption of good 1. And in the optimum, these two values must be equal. So we can summarize it. If the optimality condition holds for a consumption bundle x1, x2, the household is willing to pay just as much for an additional unit of good 1 as this unit costs. Let us have a look at these interpretations graphically. Here we see the blue budget line and the green optimal indifference curve. The optimal consumption bundle is represented by O here. It corresponds to x1 star and x2 star. If we are on this indifference curve, then there are 2 intersection points with the budget line. One in A, one in B. For an extra unit of good 1, in A, the household would agree to give up more units of good 2 than necessary. The absolute value of MRS in this point would be larger than the price ratio P1 over P2 here. You see, the indifference curve in point A is steeper than the budget line. Hence, this is not optimal. In B, the household will agree to give up less units of good 2 than necessary. So here, the MRS, the absolute value of MRS, is smaller than P1 over P2. The indifference curve in point B is flatter than the budget line. This is also not optimal. In O, the household would agree to give up as many units of good 2 as necessary. So this is then our optimal consumption point. And at this point holds the absolute value of the marginal rate of substitution is exactly equal to the price ratio P1 over P2. Let's summarize this in a nutshell. The MRS is this negative ratio of the first order partial derivative with respect to x1 divided by the first order partial derivative with respect to x2. The marginal rate of substitution reveals the willingness to substitute one good for the other. The marginal rate of substitution is the slope of an indifference curve. With strictly convex preferences, the absolute value of the marginal rate of substitution decreases along the indifference curve with an increasing consumption of good 1. This means that the slope of the indifference curve is not constant. The marginal rate of substitution is changing from one point to another on the same indifference curve. And what we also can state is that the marginal rate of substitution is the negative ratio of the marginal utilities of the goods. Let us deal with marginal utilities. What is it? The marginal utility is the partial derivative of the utility function with respect to a certain good. So here you see MUI is the partial derivative of the utility function with respect to xi. It has an economic interpretation. It tells us by how much will the utility change if the number of the good I is increased while all the other amounts of the other goods remain the same. So the MRS is nothing else but the negative ratio of the two marginal utilities of the two goods. This is a pretty nice condition, which we often can compute if the utility function produces well-behaved indifference curves, which are strictly convex and monotonic. However, the optimality condition does not always yield the optimal consumption bundle. With convex but not strictly convex, and with not differentiable indifference curves, we can have optimal consumption bundles for which this optimality condition does not hold. We will deal with this in one of our tutorials. Let us now have a look at the algebraic solution for the household optimization problem. With utility maximization, we need to maximize the function u of x1 and x2 subject to the budget constraint. We know how to do this. We have learned the Lagrangian optimization method in mathematics. So, let us write down the Lagrangian function, writing down first the objective function, and then subtracting lambda times the rearranged constraint, p1x1 plus p2x2 minus m. First order conditions are that all first order derivatives of the Lagrangian function with respect to all the arguments must be equal to 0. Here we see that. Now, let us rearrange the first two equations here to bring lambda to one of the sides. What we see here are equations 1 and 2, where lambda times the price is on the right side of the equations. And what you also can see here, equation 3, is nothing else than our initial budget constraint. Let us rearrange the first two equations, plugging them into each other, and we see that what we get here from the first two equations is nothing else but our optimality condition. The absolute value of the MRS is equal to the price ratio. So if you are dealing with a concrete function, at this point you are able to rearrange the equation absolute value of MRS equal to the price ratio such that you have x1 on one side and x2 on the other side. This equation will state the relationship that must hold between the consumption amounts of these two goods in the optimum. So, rearranging this, we get an expression for x1 depending on an x2, for instance. Now we can plug it into our budget constraint, and the result of this calculations will be the so-called Marshallian demand functions. The Marshallian demand functions give us the optimal amount of the two goods depending on the prices and the income of the household. Marshallian demand functions result from a household's utility maximizing behavior subject to a budget constraint. They always depend on the goods prices P1, P2, and on the household's budget M. Using the Marshallian demand functions, we can construct the so-called indirect utility function. For this purpose, we just take the expressions that we have got for x1 star and x2 star and plug them into our initial utility function. The result will be the indirect utility function, denoted with v here. The indirect utility function will not depend on x1 and x2 anymore, but instead it will only depend on p1, p2, and m, and hence represent the optimal utility depending on the prices and the income of the household. Let us now have a look at the Lagrangian multiplier. It has a very important economic interpretation. Let us start with the indirect utility function. We know how it's constructed. You can see it here. Let us differentiate it with respect to m. The result you see here. We need to apply chain rule here twice to get the expression on the right side of this equation 4. Let us now plug in 1 and 2 into this equation such that we get this expression, lambda times p1 times the derivative of the Marshallian function with respect to m plus lambda times p2 times the derivative of the Marshallian function of good 2 with respect to m. Here we can factor out lambda, which will result in equation 5. Now, what is the term within the brackets here in equation 5? Well, we can find out what it is. According to the budget constraint, it holds that P1 times the Marshallian demand for good 1 plus P2 times the Marshallian demand for good 2 is just equal to our budget. Differentiation with respect to m will yield the following expression. The left side is just the term that we had in the brackets, and on the right side we take the first derivative of m with respect to m, so it's just 1. So we can infer that in the equation 5 on the previous slide, we can substitute the whole expression in brackets by 1. Doing so will result in equation 5, where on the right side is only lambda left. What we see here is that lambda has the economic interpretation of the marginal utility of income. Lambda is the marginal utility of income. If a household's income increases by 1 monetary unit, the household's maximal achievable utility will change by the value of the Lagrange multiplier lambda. Let us now have a look at expenditure minimization as an algebraic solution. Here we are changing the objective function for the expenditure function, and the constraint now is here to achieve a certain fixed utility level u bar. We know that in the expenditure minimization problem, just as in the utility maximization problem, in the optimum must hold our optimality condition, MRS is equal to minus P1 over P2. Constructing it will result in an equation which we can rearrange such that we have x1 star on the one side and x2 star on the other side. Now we use this equation, plug it into our constraint, and the result will be the so-called Hicksian demand functions. Hicksian demand functions are different from the Marshallian demand functions because they depend not on m, but on the utility u. The Hicksian demand functions result from the individual expenditure minimization behavior of a certain household, subject to a target utility level. They always depend on the prices P1, P2, and on the household's utility U. The expenditure function can be computed from the Hicksian demand functions. For this purpose, we just take our budget equation and plug in the Hicksian demand functions instead of the x1 and x2. We denote it by E. This function, E, depending on P1, P2, and U, is the expenditure function, and it tells us the optimal amount of money that the household has to spend to consume the optimal consumption bundle, depending not on the amount of goods that the household wants to consume, but on the prices and the utility level of the household. Let us now revisit duality. In utility maximization, the bundle x1 star and x2 star maximizes the utility for the available budget m star. U star, which is the resulting utility level in the optimum, is then just a value of the indirect utility function v depending on p1, p2, and m star. And this is the maximum utility that can be achieved spending the budget m star. In the expenditure minimization, on the other hand, the bundle x1 star, x2 star minimizes the expenditure for the target utility level. M star, which is the optimal expenditure in this case, can be computed by plugging in P1, P2, and the optimal utility level, or the target utility level, into the expenditure function. M star here is then the minimum expenditure to achieve the target utility level. There are certain useful identities which duality implies. For all P1, P2, M, and U hold the following. Plugging in the indirect utility function into the expenditure function will result in M. Plugging in the expenditure function into the indirect utility function will result in U. Plugging in the indirect utility function into the Hicksian demand function will result in the Marshallian demand function. Plugging in the expenditure function into the Marshallian demand function will result in the Hicksian demand function. Let us summarize what we have learned today. A consumer's optimal choice is that consumption bundle in the consumer's budget set that lies on the highest indifference curve. With utility maximization, we mean to find the consumption bundle that yields the highest utility given a certain budget. With expenditure minimization, we mean to find the lowest expenditure level that is necessary to consume a consumption bundle that yields a certain utility level. If an inner solution exists and indifference curves are monotonic, convex, and differentiable, the optimality condition MRS is equal to negative price ratio yields the optimal consumption bundle. The MRS, marginal rate of substitution, is the slope of an indifference curve. It reveals the willingness to substitute one good for the other. The MRS is the negative ratio of the respective goods' marginal utilities. Good I's marginal utility is the amount by which the utility changes if the household consumes one more unit of good I. And finally, the Lagrange multiplier lambda is the marginal utility of income. Then we have derived the demand functions of a household. The Marshallian demand functions and the indirect utility function result from individual utility maximization subject to the budget constraint, and they depend always on P1, P2, and M. The Hicksian demand functions and the expenditure function result from the individual expenditure minimization subject to a target utility level. These will always depend on P1, P2, and U. The relationship between utility maximization and expenditure minimization of a private household is called duality.